Hello again. So this is another example in Sedra's book again, and it was basically also homework 19. So in that example, it's a reverse way of analysis. Again, we have an amplifier, and this amplifier is also a common emitter because the input is connected to the base, and the output, which is RL here, is connected to the collector. Why the analysis here is reversed? Because we are given the current, like IE, for example, and the voltage VC, and the resistors now are required, RC and RE. Okay, so we're gonna find those, then we go back, to the AC analysis afterwards. So let's start by the DC analysis. So in the DC analysis, we cancel all, we cancel, of course, all the AC sources, which is one source here, V signal, and we consider any capacitor as an open circuit. So the circuit will be reduced to the following. We have here -5. You have here a 5. Then you have our signal, and we canceled the V signal source, so it become grounded. So our signal now is connected to the ground, between the base and the ground. Here is RE, which is required, and here is RC, which is also required. But we know VC is equal to 1 volt. We know IE, it is 0.5 milliampere. So let's start by RE. RE is in this loop here. One say there is no loop here because maybe he's confused by the -5. So you can just remove this -5 and put a battery like this. It's -5. So let's do a Kirchhoff for that loop here. So you have here the -5. You have here IERE. You have here the 0.7. Remember VBE. Then you have IB, or so IB is flowing in that way. So the voltage it produces, it will be in the opposite way. So it goes, the same directions as the -5, the 0.7, and also IRE. So plus IB are signal equal to 0. So from that, remember that IE and IB and IB are related. IB is equal to IE over beta plus 1 or beta, because beta is 100 here. So that's, let's check now. So -5 plus IE is known, which is 0.5 milliamperes. RE is required or unknown. 0.7 is known, of course. And IB is just 0.5 milli over 100, 101. And our signal is known. It's 2.5 kilo ohms equal to 0. So we have here one unknown, which is RE. So from that, we can get RE. RE is 8.575 kilo ohms. This is number 1. Now we want to get RC. IC first is equal to IE, approximately, of course. It's equal to alpha IE if beta is big, alpha is 1, approximately, so IC is equal to IE, which is basically half milliamperes. IC is flowing in that direction from the 5 to the collector VC, which is 1 known over RC. So minus 5 minus 1 over RC equal to half milliampere. So only RC here is unknown. So from that, can determine RC. It will be 8 kilo ohms, which is 4 over half, of course, 8 kilo ohms. Okay. Also in the homework, VB was required. VB is the voltage at, the base here, the voltage of that point. And here you have two options. You have two branches here. You can say that VB, you can say the following. You can say, let me do 3 a little bit lower. You can say that VB equal to 0.7 plus IE RE plus the minus 5 or minus 5, Or you can say also, whatever you like, that it's a voltage, across our signal. But the minus the voltage across our signal. I mean, you can say that IB, which flows from the ground to VB. So 0 minus VB over RB. IB is known, which is, half milliampere, which is IE over beta, half milli over 100. VB is, RB is known. This is our signal, not RB, Our signal here. Our signal is known, 2.5 kilo ohms, and you get VB. And I prefer that one because it's shorter. Okay. One may do both, and he will notice some, discrepancy. So if you calculate VB, IB from here and from here, you will find that there are some, differences. They are close to each other, but not exact. That's because we do everything with approximation here. So don't expect that we're gonna get exactly the same numbers from both branches. No, there will be some, minor differences, but not big, of course. Okay. So if you do that, it will be minus 0.0125 volt. And again, VB here is negative, but we don't care about that. What we really care is that IB is positive. So VB can be negative, VC can be negative, VE can be negative, but IB, IC, IE must be positive numbers as long as the transistor is working either active or saturation. Even in cutoff, it cannot be negative. They must be 0, Okay, that's basically, the DC part. Finally, it was required GM and R by. GM is VT, IC, over VT. Both are known. 25 millivolt for VT and IC is half. So it's half over 25 multiplied by 10, 5 over 250, 5 over 1. So here this will be 51 over 50, which is 0.02, or 20 milli ohm minus 1. Or 0.02 ohm minus 1. Number 5, R by, because we're going to use it. We can use R by or GM, in AC, that's fine. R pi is VT over IB, 25 milli, and the IB is half milli amperes over 100. So the 100 will go to the numerator. So that will be 500. Will be half a kilo ohms or 5 kilo ohms. Okay, that's basically the DC part. Now number 2, the EC analysis. EC analysis. In the analysis, what we do is we cancel the DC sources. We have here 2 sources. We have the -5 and the 5. And again, to cancel a DC source, we cancel its effect. So we're gonna short it. We're gonna short the 5 and the -5. Okay, and we're gonna short the capacitors as well. So let's draw the circuit after we do that. So we're gonna have RC. This will be ground. RE and then a ground. And this capacitor will be short as well. So we're going to have a branch like this. And then this will be short. So we're going to have RL like this. Here is RC. This is RE. And there is no other DC sources or capacitors. So we have here V signal and R signal. That's it. Before we go and replace the transistor by its equivalent circuit, remember here RE is parallel with 0. So that short circuit will cancel RE. It's like this. So 0 parallel with any resistor is equal to 0. Okay. So we're gonna replace the transistor by its equivalent circuit. Beta IB, emitter, base, collector, R pi, and here is IB. Then connect to that. Now the emitter, because we canceled RE, is connected to ground, which will make the analysis really easy. Here is a collector. It's connected to 2 branches, RC and RL. And here is VO. Here is the base, just 1 branch, which is our signal. And this is really very simple circuit to analyze in AC. Okay. So let's start by our input. Our input is that resistor between these 2 points, this point and the ground here. Okay, and it's really easy. It's equal to R pi, because again, this circuit, this part of the circuit is isolated from that part of the circuit, because they are connected in just 1 point, which is the ground. So they don't affect each other. Okay. Number 2, so you can just remove that part away. So our input is just R bar. Number 2, AV naught. Or let's get AV first. Let's get EV and then take the limit and get EV naught. So in the previous example, we get EV naught and we get EV, okay, separately. Now we get EV first, then we take the limit, we can get EV naught. Okay, so EV is the gain when our signal equal to 0, and RL, RL is there, so we can just, just our signal, just make our signal equal to 0. Okay, so you can, let's let's divide this part here too. We don't need this. Yeah. Here is the input. Of course, the input here is just equal to V signal. Here is R by, okay. Here is RB. So the AV here is equal to VO over Vn, and Vn is of course is equal to V signal. So VO is the voltage across these two resistors, the parallel combination. This parallel combination has a current equal to beta IB. So this is equal to minus beta IB or C parallel RL, because beta IB is flowing from bottom to up, but VO is positive, negative to positive. And V input is the voltage across that resistor from that point, it's a ground, to that point is a, so it's equal to IB R by. So simply AV is equal to R by, IB will go away with IB. So we're gonna end up with minus beta or C parallel RL over R by. You can write it in that way, minus beta over R by RC RL over RC plus RL. Now, number 3, AV naught. AV naught is again when there is no load, or the load is equal to infinity. So we can say its limit or load equal to infinity, or limit, approaches infinity for AV. So that will be equal to the following: limit RL approaches infinity minus beta R pi. Divide both here by RL. So this will be RC. This will be RC over RL plus 1 RL over RL. Now you can put RL equal to infinity. If you put RL equal to infinity, that guy, or that term will be 0. So that will be minus beta over R by beta RC over R by. That's it. Always the difference between AV, this term that has something parallel with RL. Okay, RL will go away in AV naught, and that's AV naught. What else is required? GV. Number 4. GV is a function of AV. It's equal to AV or input plus our signal. Everything here is known. So let's put the numbers. So AV naught is equal to minus 160. I'm sorry, AV first, yeah, because we did. So AV here is minus 88.8. AV naught is much bigger, minus 160, and GV is even less than AV, it's minus 59. Always you have GV, always less than AV, less than AV naught. Always. So AV is reduced to AV naught is reduced to AV because of the effect of RL, and AV reduced more to GV because the effect of our signal. Okay, guys, that's basically homework 19 solution. Next recording, we're gonna do the rest of the BGT amplifier homeworks that we took. Thank you very much for watching this video, and see you in the next video. Bye.